The night sky is a lie. It looks still, but every point of light is telling a secret story of change. Those faint flickers and almost invisible shifts in starlight are not random noise. They are cosmic whispers, and they hold the key to understanding the universe's grandest transformations. By staying until the end, you will learn how astronomers decode these whispers to witness the birth of stars and the death of galaxies in real time. How can a star's rhythmic pulse measure the size of the cosmos? What does a tiny, repeating shadow around a distant sun reveal about worlds beyond our own? The answers are written in light, but you have to know how to listen. What do you think it means to watch the universe evolve? That patience is the astronomer's most vital instrument. For centuries, the story of the cosmos was locked in light, but we lacked the keys to read it. The breakthrough came from learning to ask two different, yet deeply connected, questions of every glimmer in the telescope. The first question is simple: how bright is it? The second is far more revealing: what color is it truly? The pursuit of these answers created the Cosmic Detective's Toolkit, a discipline built on patience and precision. It starts with photometry, the meticulous art of measuring brightness. An astronomer might fix their instrument on a single star for nights, weeks, even years, counting every photon of light that arrives. To the untrained eye, it is a point of steady light. To the photometrist, it is a heartbeat. A tiny, rhythmic dip in that steady pulse could be the shadow of a planet, 100 times smaller than its star, drifting across its face. A slow, steady brightening might signal a dying star's final, violent eruption, finally reaching us across the millennia. Every flicker is a sentence in a story. But to understand the characters in that story, you need to break the light apart. This is spectroscopy. Imagine passing sunlight through a prism, creating a rainbow. A spectrometer does this for starlight, but with impossible detail, stretching that rainbow into a barcode of thousands of lines. Each line is a fingerprint. Dark lines where specific colors are missing tell us what elements are present in the star's atmosphere: sodium, iron, oxygen. The very composition of a distant sun is written there for us to read. Even more profound, the entire barcode can be shifted toward the red end of the spectrum. This redshift is the universe's stretch mark, a direct measurement of how space itself has expanded during the light's long journey, carrying the galaxy away from us. This evolution from tool to language transformed astronomy. Early pioneers used photographic plates, where starlight would slowly etch a chemical impression over hours of exposure. Today, digital charge-coupled devices, or CCDs, capture light with such sensitivity they can detect a single photon. This leap in technology is why we now see variations that were once utterly invisible. What was once a still and silent point is now a dynamic, talking entity. With these languages mastered, we are finally ready to listen to what the cosmos has been trying to tell us all along. But to translate that whisper into a map, we needed our first key. It arrived not from the grandest telescope, but from the patient study of stars that refuse to stay still. Some stars breathe. They are not static points of fire but rhythmic hearts in the dark, swelling and shrinking over days or weeks in a continuous, predictable pulse. This pulse is written directly into their light, a gentle, repeating rise and fall in brightness that can be tracked with meticulous care. We call them variable stars, with two types becoming heroes of cosmic measurement: Cepheid variables and RR Lyrae stars. For a long time, these pulsating lights were just curiosities. Then, in the early 1900s, an astronomer named Henrietta Leavitt made a connection that would change everything. Working at the Harvard College Observatory, she studied thousands of variable stars in the small Magellanic Cloud, a small satellite galaxy of our Milky Way. Because all these stars were roughly the same immense distance from Earth, she realized their apparent brightness could be compared fairly. What she found was astonishing. The brighter Cepheid variables had longer periods, their pulses were slower and more drawn out. The fainter ones pulsed quickly. This was the period luminosity relationship. A star's true, intrinsic brightness was locked in the very rhythm of its heartbeat. Think of it like a lighthouse. If you see two lighthouses with identical flashing patterns, but one appears much dimmer, you know instantly that the dimmer one is farther away. Leavitt had found the flash pattern. By measuring the period of a Cepheid's light curve, how long it took to brighten and dim, astronomers could now calculate its true power. Then, by comparing that known power to how faint it appeared from Earth, they could work out the distance with stunning precision. This turned variable stars into the universe's first reliable standard candles. Suddenly, a subtle variation in light was not just a curiosity, it was a cosmic yardstick. This single discovery allowed Edwin Hubble, just a few years later, to measure the distance to the Andromeda Galaxy and prove it was an island universe far beyond our own Milky Way. Later, by finding Cepheids in even more distant galaxies and seeing their light redshifted, Hubble revealed the universe itself was expanding. The entire modern scale of the cosmos, from our galactic neighborhood to the visible horizon, was built on the foundation of measuring these gentle, rhythmic pulses in the night. It was the ultimate proof that the smallest variations in light could reveal the grandest truths. The rhythmic pulse of variable stars gave us a map of cosmic distances, but it was a silent map, showing only where things were, not what might live there. The next great whisper from the light would change that entirely, transforming distant points into solar systems. It begins with a single, almost imperceptible flicker in the steady glow of a star. Picture a light curve, that meticulous graph of a star's brightness over time, tracing a perfectly flat line. Then, for a few hours, the line dips, just a tiny amount, before rising perfectly back to where it started. It is as if a tiny, precise moth has fluttered in front of a brilliant street lamp 1,000 miles away. This is the transit method, and that microscopic dip is the shadow of a world orbiting another sun. The challenge of seeing this is almost beyond comprehension. A giant planet like Jupiter, passing in front of a sun like ours, blocks only about 1% of the star's light. An Earth-sized planet blocks a mere 0.01%. Detecting that is like trying to notice a single grain of sand removed from a vast, endless beach. To find these whispers, astronomers had to stop looking at stars one by one. They built missions like Kepler and TESS, the Transiting Exoplanet Survey Satellite, which are essentially cosmic surveillance cameras. They stare at vast patches of the sky, monitoring the brightness of hundreds of thousands of stars simultaneously, for years, waiting for that telltale, repeating dip. It is a triumph of patience and digital precision. When that dip is found, the light curve itself begins to speak. The depth of the dimming tells us the size of the planet relative to its star. A deeper dip means a larger planet. The duration of the dip, how long the shadow lasts, reveals the length of the planet's year and the shape of its orbit. But the true magic happens in the moment of transit itself. As the planet passes in front of its star, a tiny fraction of the star's light filters through the very edges of the planet's atmosphere, if it has one. By breaking that filtered starlight into a spectrum, astronomers can search for the fingerprints of molecules. A spike indicating sodium might suggest a puffy, hot world. The signature of water vapor could hint at something more temperate. We are not just detecting shadows anymore. We are beginning to sniff the air of alien worlds from across the galaxy. What began as a faint, periodic flicker becomes a data point in a new kind of census. A growing catalog of distant realms where the conditions for life, as we understand it, might just exist. The transit method reveals new worlds, but the final whisper comes from a star's last defiant cry. A supernova is not just a point of light that appears and fades. It is a conversation, and its afterglow tells a story we are only beginning to translate. For a brief moment, a single dying star can outshine its entire host galaxy, a catastrophic beacon visible across the cosmos. Ancient astronomers saw these events as the sudden birth of new stars, but we now know they are spectacular endings. The initial flash is only the first word. The true message is carried in the light curve, the meticulous record of how that brilliant point fades over weeks and months. This fading light is the echo of the explosion itself, and its shape holds precise information about what died and how. Among these cosmic explosions, one type has become a cornerstone of modern cosmology, the Type 1 a supernova. These are not the death of massive stars, but the thermonuclear detonation of a white dwarf, the dense, Earth-sized core left behind by a sun like ours. What makes them so valuable is their consistency. Because they all explode at nearly the same critical mass, they all reach nearly the same peak brightness. This makes them phenomenal standard candles, even more powerful than Cepheid variables, allowing us to measure distances to galaxies billions of light years away. But the universe always adds nuance. Astronomers notice that not all Type 1 a light curves are identical. Some fade a little faster, others a little slower. These subtle deviations are not errors, they are clues. A slower decline might mean the explosion was more powerful, or that it produced a different mix of radioactive elements whose decay powers the afterglow. By studying these minute differences in the fading pattern, scientists can calibrate the supernova's true peak luminosity with incredible precision. It is like recognizing that two identical-looking flashlights might have batteries of slightly different quality, and adjusting your distance estimate accordingly. This calibration is not an academic exercise. It is how we measure the accelerating expansion of the universe. By comparing the calibrated brightness of these supernovae to their immense redshift, astronomers made the shocking discovery that the universe's expansion is speeding up, driven by a mysterious force we call dark energy. The precise, fading light of a star's death, a whisper of change recorded over months, thus becomes our most powerful tool for interrogating the ultimate fate of all things. In its gentle decline, we find the signature of the force that will determine the cosmos's final chapter. The fading light of supernova reveals the fate of the cosmos, but there is a fourth signal that whispers of the unseen. It begins with a simple, profound truth from Einstein's relativity, that mass bends the fabric of space and time. A massive object, like a star or even a black hole, does not just sit in space, it creates a curvature. Light, traveling from a distant source, must follow this curve. When a foreground object passes almost perfectly between us and a background star, that curvature acts as a natural magnifying glass. It warps and bends the light rays, focusing them toward Earth and causing the distant star to temporarily brighten. This is gravitational microlensing, and its signature is written in a uniquely pure light curve. Unlike the sharp dip of a planetary transit or the explosive peak of a supernova, a microlensing event paints a smooth, symmetric arc on the graph. The background star's brightness rises steadily to a peak as the alignment becomes perfect, then falls away in a mirror image. It is a single, graceful hum in the data. Capturing it is an exercise in cosmic luck and relentless vigilance, requiring telescopes to monitor hundreds of millions of stars in crowded fields like the galactic bulge, waiting for that one chance alignment to occur. The beauty of this signal is that it does not depend on the lensing object's own light. It reveals mass purely through its gravitational influence. This means microlensing can find the dark and the cold, objects that emit little to no light of their own and are otherwise completely invisible. It has unveiled a hidden population drifting through the galaxy. Rogue planets, worlds torn from their solar systems to wander the interstellar darkness alone, betray their presence by lensing a distant star's light. Failed stars known as brown dwarfs, too massive to be planets but too small to ignite fusion, have been counted through their gravitational touch. Theorists even propose it could detect primordial black holes, hypothetical remnants from the universe's first second, if they drift through a starfield. Each smooth, symmetric brightening is a census of the unseen architecture of our galaxy. A map written not in starlight, but in the subtle warping of space itself. It proves that to see the universe in its entirety, we must learn to read the quiet tremors in the path light takes to reach us. From the silent warping of space, we turn to the violent hearts where light is born. At the center of nearly every large galaxy, including our own Milky Way, sleeps a supermassive black hole. But some are not sleeping, they are feasting. When vast rivers of gas and dust fall toward this ultimate point of no return, they do not vanish quietly. They swirl into a maelstrom of incandescent plasma called an accretion disk, heating to millions of degrees and blazing with light across the entire spectrum. This is an active galactic nucleus, or a GN, and its light is never still. It flickers, flares, and pulses like the erratic heartbeat of a cosmic giant. By monitoring these subtle, often chaotic variations, astronomers have found a way to probe the extreme physics occurring just outside the event horizon itself. The changes are not random noise. They are a direct echo of the violent processes feeding the beast. A sudden spike in X-ray brightness might signal a dense clump of matter spiraling inward and being torn apart. A slower, rhythmic pulse in optical light could map the precession, or wobble, of the entire accretion disk as it is twisted by the black hole's immense spin. Even the powerful jets of material, shot out at nearly the speed of light from the poles of some black holes, announce their launch with a flare in radio waves. Each wavelength tells a different part of the story. The X-rays come from the searing inner disk, closest to the point of no return. The optical light emerges from farther out, where temperatures are merely that of a star's surface. The radio waves often trace the structure of the colossal jets. By watching how a flare in one band of light echoes into another with a slight delay, scientists can literally map the geography of this infernal region, measuring distances that are impossible to see directly. It is like listening to the sounds in a dark, complex machine, a clank here followed by a whir there, to understand its hidden gears. This variability is more than just a spectacle. It is a diagnostic tool for understanding how these monsters grow. The pattern of flickers can reveal how efficiently the black hole is consuming matter, and how much energy it pumps back into its host galaxy, potentially halting the birth of new stars and shaping the galaxy's evolution over billions of years. The faint, restless twinkle from a pinpoint of light a billion light-years away is, in truth, the vital sign of a galaxy's central engine, a direct line to the most powerful and transformative forces in the universe. Brightness tells us the rhythm, but color tells us the story. To understand the universe's deepest secrets, we must learn to read its rainbow. This is the domain of spectroscopy, and it begins with a simple prism. When sunlight passes through one, it fans out into the familiar bands of red, orange, yellow, green, blue, indigo, and violet. Starlight does the same, but when a powerful spectrograph stretches that cosmic rainbow across a detector, the smooth band fractures. It becomes a meticulous barcode, etched with thousands of dark and bright lines. Each line is a direct signature, a fingerprint left by a specific atom or molecule in the star's atmosphere. A pair of dark lines in the yellow part of the spectrum, that is sodium. A cluster of lines in the blue, that is the unmistakable mark of calcium. With this single tool, we can take a sample of a star's chemical composition from a billion light-years away, reading the ingredients of a sun we will never touch. But the story does not stop with a list of elements. The entire barcode can slide. If the star is moving toward us, the lines shift slightly toward the blue end of the spectrum. If it is moving away, they shift toward the red. This Doppler shift is the universe's speedometer. It is how we measure the orbital dance of binary stars, the spin of galaxies, and most profoundly, the expansion of space itself. The pervasive redshift of distant galaxies, where their spectral lines are all systematically shifted toward longer, redder wavelengths, was the key evidence that the cosmos is stretching, carrying galaxies apart like raisins in an expanding loaf of bread. Yet the most subtle whispers are found not in the position of the lines, but in their shape. A spectral line is not a perfect, sharp scratch on the rainbow. It has a profile. If that profile is subtly broadened, smeared at the edges, it can tell us the star is spinning rapidly. Its light from the approaching limb blue-shifted and the light from the receding limb red-shifted, blending together. If the line is split into 2 or 3 closely spaced lines, that is the Zeeman effect, the signature of a powerful magnetic field twisting the atoms within. And when hunting exoplanets, spectroscopy performs its finest trick. As a planet transits its star, a tiny fraction of the star's light filters through the planet's limb, skimming its atmosphere. That filtered light carries with it the faint, additional fingerprints of whatever molecules are present there. By comparing the star's spectrum taken just before the transit to the spectrum taken during it, astronomers can subtract the star's signature and be left with the whisper-thin spectrum of an alien sky, searching for the signs of water vapor, methane, or even oxygen. From a single point of light, spectroscopy builds a rich, multidimensional portrait, revealing composition, motion, magnetic personality, and even the potential chemistry of other worlds. It turns starlight into a biography. For all of human history, the night sky was a still photograph. We looked up and saw the same constellations our ancestors saw, the same fixed tapestry of stars. But this was an illusion born of our own limited perspective. The universe is not a snapshot. It is a movie, a continuous, sprawling epic of change playing out on a timescale so vast we could only see its frozen frames. That perspective has now shattered. We are entering the era of the time domain, where the sky is watched not once, but every single night. This revolution is powered by a new generation of wide-field telescopes, like the Zwicky Transient Facility scanning from California and the monumental Vera C. Rubin Observatory being built in Chile. Their mission is simple yet transformative, to map the entire visible sky over and over again, night after night for years. They are not looking for what is there, they are looking for what is different. Imagine a security camera pointed at a vast city, but instead of looking for movement, it is looking for any light that turns on, off, brightens, or fades. Every 24 hours, these observatories compare their new images to the old ones, automatically flagging anything that has varied. This creates a living, breathing map of cosmic change, a data stream of the universe's vitality. Before this, discovering a supernova was often a lucky find by an amateur astronomer. Now, these robotic surveys can detect dozens in a single night, along with a zoo of other transient phenomena. They catch the brilliant flash of a kilonova, the cataclysmic merger of 2 neutron stars that forges heavy elements like gold and platinum. They spot the sudden ignition of a young stellar object, a star's first light after coalescing from a cloud of gas. They find stars being torn apart by the tidal forces of hidden black holes. This is no longer about studying isolated events. It is about observing processes, watching the mechanisms of cosmic evolution unfold in something close to real time. We are moving from collecting specimens to monitoring an ecosystem. The static sky has come to life, revealing a universe far more dynamic, violent, and creative than we ever dreamed. And we now have a front-row seat to the show. The rhythm of the cosmos is not just in its explosions or transits, but in its music. Deep inside every star, a constant, resonant hum is born from the turbulent churning of its fiery plasma. These are not sound waves as we know them, but pressure waves, ripples of compression and expansion that travel through the stellar interior, bouncing between the core and the surface. When they reach the star's outer layers, they cause the entire globe to gently pulse, ever so slightly changing its brightness and temperature in a regular, predictable pattern. This is the star's song, and the science of listening to it is called Asteroseismology. Think of a giant bell. When you strike it, it does not just ring with a single pure tone. It resonates with a complex blend of overtones, each one determined by the bell's exact shape, size, and the material from which it is made. A star is a massive, spherical bell of superheated gas, and its internal sound waves create a similar symphony of resonant frequencies. Each distinct vibrational mode, or overtone, probes a different depth within the star. Some modes skim just below the surface, while others dive all the way down to the very heart of the nuclear furnace. By meticulously analyzing the precise frequencies and patterns in a star's light curve, astroseismologists can perform a kind of cosmic ultrasound. They can map the internal structure of a sun they will never visit. The dominant frequencies reveal the star's overall density and mass. The spacing between certain overtones tells us about the chemical composition gradient from the core to the envelope. Even the splitting of frequencies can unveil how rapidly the star's interior is rotating, which can be different from how fast its surface spins. This turns a twinkling point of light into a detailed cross-section. For stars like our Sun, this data is incredibly precise, allowing us to know its internal conditions and age with an accuracy that rivals our knowledge of Earth's own interior. For distant, ancient stars, it is a form of archaeology. By listening to the oscillations in the light of a star 10 billion years old, we can determine its mass and internal composition, which tells us what raw materials were available when it formed in the early galaxy. This stellar music is the direct echo of the engine room, allowing us to understand not just what a star looks like from the outside, but how it works on the inside, and how it will change over its multi-billion-year life. That stellar music fades as we look back in time toward the very edge of what we can see. Beyond a certain point, the universe goes dark, not in emptiness but in a primordial fog. For hundreds of millions of years after the Big Bang, the cosmos was a simple, featureless sea of neutral hydrogen gas, utterly black to our eyes. No stars, no galaxies, no points of light pierced the gloom. This was the cosmic dark age. Its end was not a single moment but a slow, rolling dawn. Somewhere in that vast darkness, the first protogalaxies coalesced, and within them the first stars ignited. These were not like the stars of today. They were behemoths, hundreds of times the mass of our Sun, burning ferociously hot and blue, and living violently short lives. Their death was as important as their birth, for they flooded the universe with something new, an intense blast of ultraviolet radiation. This radiation carried enough energy to do something profound, to strip the electrons from the pervasive neutral hydrogen atoms that filled all of space. One by one, then in growing waves, these atoms were ripped apart into their constituent protons and free electrons. The universe was being fundamentally transformed from neutral to ionized in an epic process we call reionization. It was the final major phase change of the cosmos, clearing the fog and making the universe transparent to the light that would follow. We cannot see those first stars directly. Their light is far too faint and stretched beyond recognition by the universe's expansion. So how do we witness this cosmic dawn? We listen for an echo in the fog itself. Every atom of neutral hydrogen in the universe has a signature, a very specific radio whisper. It emits a photon with a wavelength of 21 centimeters. During the Dark Ages, this faint radio hum would have been everywhere, a uniform background hiss. But as the first stars and galaxies switched on, they created growing bubbles of ionized, transparent space within the neutral fog. Imagine a block of Swiss cheese, where the solid cheese is the neutral hydrogen, and the holes are the bubbles cleared by starlight. From our vantage point billions of years later, we would see a patchwork sky in this 21-centimeter radio light. The signal from the bubbles would be absent, while the signal from the remaining neutral regions would shine through. Crucially, the expansion of the universe stretches this signal as well. The 21-centimeter emission from the era of reionization does not reach us at 21 centimeters. It is redshifted to wavelengths of meters or more, a deep, low-frequency rumble. By building vast, sensitive radio telescopes in remote locations, like the Hydrogen Epoch of Reionization Array or the Future Square Kilometer Array, astronomers are trying to tune into this ancient station. They are not looking for a single source, but for a specific pattern of faint fluctuations, a subtle modeling in the radio sky that maps the bubbly frontier of this cosmic transformation. Detecting this pattern is one of the great quests in modern cosmology. It would be a direct image of the universe's first architecture. A baby picture showing where and how the very first lights in the cosmos flickered on, ending the long night and setting the stage for everything that was to come. The cosmic soundtrack grows richer when we realize most stars are not solitary. They are partners, locked in a gravitational embrace that writes its own complex rhythm into the light we receive. This is the realm of binary and multiple star systems, where the subtle variations in brightness become a direct window into stellar relationships, from serene dances to catastrophic mergers. The most straightforward example is the eclipsing binary. Imagine two distant suns, one slightly larger and cooler, the other smaller and hotter, orbiting a common center of gravity. From our vantage point, their orbital plane is nearly edge-on. As they circle each other, each star will periodically pass in front of its partner. When the hotter star ducks behind the cooler one, we see a deep, primary dip in brightness. When the hotter star passes in front of the cooler one, we see a shallower, secondary dip. The resulting light curve is not a single, clean pulse, but a repeating, double dip pattern with a flat plateau of constant light in between. It looks like a perfectly timed celestial heartbeat with two distinct beats. This elegant pattern is a treasure trove of data. The timing of the dips gives us the orbital period, the length of the star's year. The depths of the dips reveal the relative sizes and temperatures of the two stars. But most importantly, by combining this photometric data with spectroscopic measurements of the star's orbital speeds, we can solve for their actual masses and physical radii. This is the bedrock of stellar astrophysics. Before we could measure binaries, a star's mass was largely theoretical. Now we have precise, empirical numbers for thousands of stars, which allows us to test and refine our models of how stars live, age, and die. These serene, predictable eclipses provide the fundamental ruler against which all other stellar behavior is measured. But not all stellar partnerships are so orderly. Bring the stars closer together, and the dance becomes intimate and volatile. In a system called a cataclysmic variable, a white dwarf star, the dense Earth-sized core of a dead sun, orbits so close to a normal, sun-like star that its powerful gravity begins to strip material away. This stolen gas does not fall directly onto the white dwarf. Instead, it spirals inward, forming a swirling, luminous accretion disk around it. The light from such a system is never steady. It flickers and flares erratically. You might see small, rapid flickers from turbulence in the disk itself, and every few weeks or months, a dramatic outburst where the entire system brightens by a factor of 100. This happens when too much hydrogen builds up in the disk, triggering a runaway thermonuclear reaction on the white dwarf's surface, a stellar tantrum written in light. Analyzing these wild light curves tells a story of give and take on a cosmic scale. The timing and strength of the outbursts reveal the rate of mass transfer and the stability of the disk. In the most extreme cases, if the white dwarf accumulates too much mass from its companion, it can be pushed past a critical limit and explode completely as a Type 1, a supernova. What begins as a subtle, periodic dip from a distant eclipsing binary can, in other systems, evolve into the precursor flickers of a stellar catastrophe. By decoding every flicker, dip, and flare, we witness the full spectrum of stellar relationships, understanding not just how stars exist in isolation, but how they interact, transform each other, and sometimes meet their dramatic ends together. Somewhere between the steady hum of stellar music and the epic dawn of reionization lies a signal that defies all categories. It arrives without warning, a flash of radio waves so intense it can outshine an entire galaxy, yet it is over in less time than it takes to blink. These are fast radio bursts, or FRBs, the universe's most cryptic postcards. For a single millisecond, a torrent of radio energy floods from deep space, and then it is gone, often never to repeat. The power behind such a fleeting event is staggering, equivalent to our sun's total output over several decades released in an instant. The sheer brevity tells us the source must be incredibly small, no larger than a city. For light itself cannot travel fast enough to coordinate a longer flash from a larger object. But where and what could possibly create such a focused, titanic spark? The first clues are not in the burst itself, but in the subtle way it arrives. As these radio waves race across billions of light-years of intergalactic space, they pass through a sparse sea of free electrons. These electrons act like a cosmic prism for radio waves, slowing lower frequencies just slightly more than higher ones. This causes the signal to smear out, with the highest frequencies arriving a fraction of a second before the lowest. This delay is called the dispersion measure. By calculating how much the burst has been smeared, astronomers can estimate the total number of electrons it passed through, which gives them a rough gauge of the immense distance the signal has traveled, confirming these whispers come from other galaxies. This dispersion is the first whisper within the shout, a fingerprint of the lonely vastness the burst had to cross to reach us. The mystery deepened when some bursts began to repeat. Unlike the one-off events, these repeaters send out multiple flashes, sometimes in erratic patterns, other times with a discernible periodicity. Even more intriguing, the individual bursts themselves can have fine structure. When the light curve of a millisecond burst is stretched and examined with nanosecond precision, some reveal multiple peaks, or a downward drifting pattern in frequency, like a cosmic slide whistle. These are not simple explosions, they are intricate events. Each tiny wiggle in that impossibly fast light curve is a vital clue, constraining what the source could possibly be. The leading suspect is a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth's. Theorists suggest a starquake on such an object's crust could release a cataclysmic snap of magnetic energy, launching the burst. The repeating patterns could come from a magnetar in a messy, debris-filled environment, with orbiting material periodically triggering outbursts. Yet some bursts are so energetic, they push the limits of what even a magnetar is thought to be capable of, hinting at more exotic origins, perhaps the violent merger of ultra-dense objects or the catastrophic collapse of a highly magnetized star into a black hole. Every new detection, especially those with complex internal structure, adds a piece to this high-energy puzzle. In their fleeting, brilliant signatures, we may be witnessing a previously hidden phase in the life cycle of the universe's most extreme objects, or tapping into a realm of physics we have not yet begun to understand. But the universe writes its history in more than just starlight and radio whispers. There is a subtler canvas, a nearly perfect backdrop of cold radiation that fills every corner of space, the afterglow of creation itself. This is the cosmic microwave background, the CMB, a faint microwave hum left over from the hot, dense infancy of our universe. For decades, it was seen as a smooth, uniform sea, a baby picture of cosmic structure. But its perfect smoothness is an illusion. Look closely, and you will find shadows and imprints, subtle scars left by the universe's later growth. One of the most profound of these scars is named for the scientists who predicted it, the Sunyaev-Zeldovich effect, or SZ effect. To understand it, picture the CMB as a sea of ancient photons, particles of light that have been traveling undisturbed for over 13 billion years. Now imagine one of these primordial photons on its endless journey, passing through a galaxy cluster, the universe's most massive gravitationally bound structure. The space between the galaxies in a cluster is not empty. It is filled with a superheated plasma, a thin gas of electrons so hot it glows in X-rays. As that ancient CMB photon flies through, it has a chance to collide with one of these energetic electrons. In the scattering, the photon steals a tiny amount of energy from the electron. This interaction is incredibly subtle, but it leaves a distinct fingerprint. It shifts the photon's wavelength, bumping it from the microwave part of the spectrum slightly toward higher energies. Across the entire cluster, billions of such scatterings occur. The result is a specific, cold spot on the microwave sky. In the precise frequency where the CMB shines brightest, The cluster appears as a slight shadow, a dimming. At higher frequencies, it appears as a bright patch. This dual signature is the unmistakable mark of the SZ effect. Its power lies in its independence. Unlike optical light that dims with distance, or X-ray emission that can be absorbed by foreground gas, this scattering signal does not fade as the cluster gets farther away. The distortion is imprinted directly on the CMB background, and its strength depends only on the number of hot electrons the photon C must pass through. This makes the SZ effect a phenomenal tool for taking a census of the most massive things in the universe, all the way back to when clusters were first assembling. Astronomers use sensitive microwave telescopes to scan the sky, not for points of light, but for these specific spectral distortions. Each detected patch is a signpost marking a colossal reservoir of hot gas, and thus, a massive galaxy cluster. But the story does not end with finding them. The shape and detailed texture of the SZ signal itself are a map. A smooth, symmetrical signal suggests a relaxed, mature cluster that has not experienced a major collision in billions of years. A lumpy, irregular distortion, however, tells a tale of violence. It reveals clusters caught in the act of merging, their vast clouds of plasma slamming together at millions of miles per hour, creating shock waves and turbulence that stir the intergalactic gas. By reading these subtle variations in the microwave shadow, we can reconstruct the history of how these cosmic cities formed and grew, not from their starlight, but from the echo their hot breath leaves on the oldest light in existence. The light we have been listening to holds one final, hidden dimension. Beyond its brightness and its rainbow of colors, light waves also have a direction, a specific orientation in which they vibrate as they travel through space. This property is called polarization, and it is a subtle pointer that can be altered by the very fabric of the cosmos itself. The most common cosmic polarizer is something seemingly mundane: interstellar dust. These microscopic grains, forged in the atmospheres of dying stars and scattered across the galaxy, are not perfectly round. They are more like tiny needles or rods. And just as iron filings align with a bar magnet, these elongated dust grains tend to align themselves with the Milky Way's vast, invisible magnetic fields. When starlight passes through these clouds of aligned dust, the grains preferentially absorb and re-emit light vibrating in one direction over another. The starlight that emerges is polarized, its waves now vibrating in a plane aligned with the local magnetic field. By meticulously measuring the polarization of starlight from millions of stars, astronomers can trace the lines of force. They are not seeing the magnetic field directly, but they are seeing its shadow, its imprint on the light. This creates a three-dimensional map of our galaxy's magnetic skeleton, revealing how these invisible lines weave through spiral arms, channel cosmic rays, and influence where new stars can form. It is a ghostly blueprint, drawn in the faint alignment of ancient starlight. This principle scales up to the universe's very first light. The cosmic microwave background, that ancient afterglow, is also polarized. Its polarization comes from the last scattering of light off the hot plasma of the infant universe, and it carries two distinct patterns. The first, called E-mode polarization, has been mapped in exquisite detail and confirms our standard model of cosmic evolution. But the second pattern is the holy grail of cosmology, B-mode polarization. This is a faint, curling, swirling pattern in the polarization map, like the fingerprints left on a soap bubble. Theorists predict these swirls were not imprinted by the hot plasma, but by something far more primordial: gravitational waves from the universe's inflationary Big Bang. In the first fraction of a second of existence, the cosmos is thought to have undergone a period of hyper-accelerated expansion called inflation. This violent stretching of space-time itself would have generated ripples in the fabric of reality, primordial gravitational waves. As these waves passed through the hot plasma of the early universe, they would have gently sheared and twisted the polarization of the CMB light, leaving behind that distinctive swirling B-mode signature. Detecting this signal is one of the most difficult challenges in all of science. It requires instruments of unbelievable sensitivity, placed in the most pristine environments on Earth, high on the Antarctic plateau or even in space, to filter out any contaminating signal from our own galaxy's dust. Finding that subtle, swirling variation in polarization would be a direct message from the universe's first instant, a whisper from the moment of its most explosive and energetic birth, confirming a chapter of cosmic history written when time itself was just beginning. That faint, swirling signature in the CMB's polarization points back to the universe's first chaotic moments, but the story of chaos continues. The cosmos is filled with engines, and they all run on the same violent fuel. From the birth of a star to the feast of a black hole, the universe is powered by accretion, the relentless fall of matter onto a central gravitational anchor. This process is never smooth. It is a turbulent, clumpy, and inherently unstable cascade, and its signature is written in flickering light across every wavelength. The journey of that flicker begins in stellar nurseries, vast clouds of gas and dust where gravity begins to pull matter together. As a dense core collapses, it forms a spinning disk of material feeding a central protostar. This young stellar object is not yet burning hydrogen in its core. Instead, it shines from the sheer violence of its birth, from the gravitational energy released as gas and dust rain down upon it. The light from this process is not steady. It flickers and flares, especially in the infrared and optical bands. A sudden brightening might last for days or weeks, not from the star itself, but from a massive clump of material, a planetary building block the size of a solar system, spiraling inward from the disk and slamming into the stellar surface. Each flicker is a snapshot of the construction process, a real-time view of how a star gathers its final mass, and how the leftover debris in the disk begins to coalesce into planets. The instability is built in, as the delicate balance between gravity pulling material in and magnetic pressure flinging it back out creates a chaotic, pulsing engine. This same principle of chaotic feeding scales up to the most extreme environments imaginable. Around a stellar mass black hole or a neutron star in a binary system, gas stripped from a companion star forms a searingly hot, whirling accretion disk. The physics here are pushed to the limit, with temperatures soaring to millions of degrees and emitting furious X-rays. In these regions, the flickering becomes frantic, changing on timescales of milliseconds. This is not random noise. Embedded within the chaotic X-ray light curve are subtle, repeating patterns called quasi-periodic oscillations. These are not perfect, metronomic ticks like a clock, but rather preferred rhythms in the turbulence, a hum or a warble that appears and disappears. Their very existence is a direct probe of spacetime itself. The frequency of these oscillations is thought to be tied to the orbital motion of blobs of plasma at the very innermost stable orbit, just outside the black hole's event horizon. By studying these rapid, quasi-periodic flickers, physicists can map the geometry of this extreme region. Different frequencies might correspond to the spin of the black hole warping the inner disk, or to vibrations within the disk itself. It is a way of using light as a sonar ping into the abyss, testing the predictions of Einstein's general relativity under conditions of crushing gravity and unfathomable density. Whether tracing the gentle, clumpy infall onto an infant sun or decoding the millisecond X-ray stutter from the edge of oblivion, the flicker of accretion reveals a universal truth. The cosmos builds and destroys through messy, unstable, and gloriously informative cycles of collapse. And by listening to their rhythms, we learn how everything, from a star to a galaxy, is fueled. This intricate chain of measurements forms a cosmic distance ladder, and its most crucial rungs are carved from the subtle variations in light. Our understanding of the universe's vast scale is not a single measurement, but a careful, interconnected climb. Each step relies on the one below it for calibration, and variability provides the firmest footholds. It begins in our galactic neighborhood with the rhythmic pulse of Cepheid variable stars. By using Henrietta Leavitt's period luminosity relationship, astronomers could determine their true brightness and thus their precise distance. This allowed them to accurately measure nearby galaxies like Andromeda for the first time. But Cepheids, brilliant as they are, fade from view at immense distances. To reach farther, we needed a brighter beacon. This is where those meticulously studied Type 1 supernova enter the story. Because they all explode with nearly the same intrinsic brightness, they are phenomenal standard candles. But to use them with confidence, we first had to find them in galaxies whose distances we already knew. Those nearby galaxies, whose distances were pinned down by their resident Cepheid variables, became the training grounds. By observing Type 1 supernova in these calibrated galaxies, astronomers could fine-tune their understanding of the supernova's exact peak brightness, accounting for the subtle differences in their light curves. Only then could they confidently use these stellar explosions to measure galaxies billions of light-years away. This latter, built step by step from variable stars to exploding stars, gave us our first reliable map of an expanding cosmos. Yet this map has revealed a puzzling tension. When we use this ladder of standard candles to measure the current expansion rate of the universe, known as the Hubble constant, we get one very precise number. But when we use the pristine snapshot of the early universe, the cosmic microwave background, to predict what that expansion rate should be today, we get a different, equally precise number. The two methods, both exquisitely refined, disagree. This is not a small discrepancy. It is a significant gap that has persisted despite decades of increasingly precise observations. It means one of two things. Either there are tiny, unaccounted for systematic errors in how we measure the light curves of our most trusted standard candles, perhaps in how dust affects their light or how we model their explosions. Or the universe is trying to tell us something new. This tension could be a hint of unknown physics, a shadow of some exotic force or particle that influenced the expansion history of the cosmos in a way our current models do not include. The entire edifice of cosmic scale, from our local stars to the edge of visibility, rests upon our ability to correctly interpret every flicker and fade in the light of these distant messengers. A misinterpretation of a subtle dip in a Cepheid's pulse, or a misreading of a supernova's decline, could send our understanding of the universe's size and fate spiraling in the wrong direction. The quest to resolve this tension is now one of the most urgent in cosmology, a direct challenge issued by the quietest variations in the most distant lights. That cosmic distance ladder, built on flickering starlight, must pass through a universal haze. Interstellar dust is the astronomer's ancient foe, a veil of microscopic grains that dims, reddens, and scatters the light of everything behind it. For centuries, it was simply an obstacle, a frustrating fog that hid the true depths of the Milky Way. Yet this apparent nuisance is now understood as a vital storyteller, its very interference revealing the intimate details of cosmic structure. These are not simple specks of dirt. They are complex grains, smaller than a wavelength of visible light, forged in the violent atmospheres of dying stars. Their cores are often rocky silicates, like tiny fragments of glass or sooty carbon compounds, the same stuff in pencil lead. Their shapes are irregular, more like jagged flakes than perfect spheres. When starlight encounters this dust, a careful sorting occurs. Shorter wavelengths of light, the blues and violets, are scattered away from the line of sight, much like our own sky scatters sunlight to appear blue. The longer wavelengths, the reds and oranges, pass through more easily. This is why the sun appears redder at sunset, and why distant stars look more reddish than they truly are, an effect called interstellar reddening. The degree of this reddening is not random. By measuring how much a star's light has been dimmed and reddened across many different wavelengths, astronomers construct an extinction curve. This curve is a unique fingerprint. A steep curve suggests the dust along that line of sight is dominated by very small grains. A flatter curve points to larger grains. By comparing curves from thousands of stars, we can map not just where the dust is, but what it is made of and how it has been processed by shock waves and stellar winds over billions of years. The dust is no longer a blurry curtain. It is a detailed chemical map of the galaxy's recycling plants. But the story does not end with absorption. That stolen starlight does not vanish. These tiny grains, warmed by the radiation they absorb, re-radiate the energy back out, but at much longer, infrared wavelengths. A dark, opaque cloud in visible light can glow with a gentle, warm radiance in the infrared. This transformation is revolutionary. Where optical telescopes see only a blank void in the constellation Orion, infrared eyes see the Orion Nebula, a brilliant stellar nursery blazing with the heat of newborn stars, its dust cocoons shining from within. On a galactic scale, this faint infrared glow becomes a census of hidden activity. Some galaxies, known as starbursts, are enshrouded in so much dust that almost all their visible light is trapped. Yet their furious rate of star formation heats the dust to such a degree that they become some of the brightest objects in the entire universe in the infrared. By surveying this subtle background glow across the cosmos, we trace the history of star formation itself, following the dusty fingerprints of creation through time. The very material that obscures our view also illuminates the hidden engines of cosmic evolution, whispering the secrets of what lies within the shadows. These whispers from dust and light are about to grow louder. The next decade will see the launch of a new generation of cosmic listeners. Observatories of such scale and sensitivity, they will transform every subtle variation into a shout. On a mountain peak in Chile, engineers are assembling the mirror of the Extremely Large Telescope, or ELT. Its primary mirror will be nearly 40 meters across, a colossal honeycomb of almost 800 individual segments that will gather more light than all of the world's major optical research telescopes combined. This is not just a bigger eye on the sky, it is a deeper ear to the cosmos. Its immense photon-collecting power means it will see objects 100 million times fainter than the human eye can perceive. For the study of light variations, this is revolutionary. The ELT will detect the rhythmic pulse of Cepheid variables in galaxies at the very edge of the observable universe, extending our cosmic distance ladder into uncharted territory. It will watch the flickering accretion disks around supermassive black holes in the earliest galaxies with stunning clarity, tracing their growth when the universe was in its infancy. Its spectrographs will be so precise they could measure the speed of a walking human on the surface of a distant exoplanet, allowing us to not just detect an atmosphere, but to map its global wind patterns by watching how spectral lines shift and blur as the planet rotates. In space, another giant is preparing for launch. The Nancy Grace Roman Space Telescope will carry a mirror the same size as Hubble's, but with a field of view 100 times wider. Where Hubble is a brilliant spotlight examining one tiny patch of sky in exquisite detail, Roman will be a floodlight, capturing panoramic portraits of the cosmos with the same sharpness. Its primary mission is a statistical one, to take a vast cosmic census. It will discover thousands of new exoplanets through the transit method, watching for those telltale dips across hundreds of thousands of stars simultaneously. But its true power for subtlety lies in its microlensing survey. By staring continuously at the crowded star fields at the heart of our galaxy, Roman will catch hundreds, perhaps thousands, of those smooth, symmetric brightenings that betray the presence of rogue planets, free-floating worlds with no sun of their own. It will weigh these dark wanderers, building a complete inventory of the galaxy's hidden, nomadic population. Together, these observatories will push spectral analysis into a new realm. The ELT, with its colossal light-gathering power, will be able to take the spectrum of an Earth-sized planet orbiting a small, dim red dwarf star. It will look for the subtle absorption lines of water vapor, methane, and oxygen in that whisper-thin slice of starlight filtered through the alien air. The pattern of these lines, their relative strengths and combinations, could hint at chemical processes that are out of equilibrium, a potential sign of biology. We will move from detecting atmospheres to characterizing them, from finding planets to beginning the long, careful search for signs that we are not alone in the cosmic story. This next phase of discovery will be written by these giants, translating the faintest cosmic murmurs into a new language of understanding, one precise photon at a time. This torrent of light will create an ocean of data, a deluge so vast it would drown any team of human analysts, the Vera Sea. Rubin Observatory alone will generate about 20 terabytes of data every single night, compiling a catalog of over 20 billion galaxies and a similar number of stars. Within that ocean, millions of those points of light will be varying, flickering, and changing. To find meaning in this flood, we have forged a new kind of partnership. We are teaching machines to see the patterns we seek, to become our tireless collaborators in the dark. This is where machine learning and artificial intelligence step onto the cosmic stage, not as replacements for human curiosity, but as its essential amplifiers. The task is monumental but precise. An algorithm is shown thousands of known light curves, each one carefully labeled by astronomers. This is a pulsating Cepheid. This is the double dip of an eclipsing binary. This jagged line is the flare of an active galactic nucleus. Through repeated exposure, the algorithm learns the subtle signatures of each class, the rhythmic mathematics of a star's breath, the geometric symmetry of an orbital shadow, the chaotic spike of a feeding black hole. Once trained, it can scan millions of new, unknown light curves in a fraction of the time a human could, sorting them into categories with astonishing speed and consistency. It performs the initial, overwhelming sift of the cosmic haystack. But these tools do more than just classify what we already know. Their true power lies in spotting the outlier, the object that does not fit any known pattern. An algorithm can flag a light curve that is just strange. Perhaps it has a dip that is too shallow and too long, or a series of pulses with a rhythm that defies known physics. These anomalous signals are the most exciting finds of all, because they may point to phenomena we have not yet dreamed of. A new class of variable star, a planet with a bizarre ring system, or the death throes of an exotic object. This synergy is the new frontier of discovery. Human intuition asks the questions and defines the mysteries. Computational power provides the brute force search through the data universe. Together, they transform that petabyte flood from noise into a structured library, a living encyclopedia of cosmic behavior where every flicker has a name, a family, and a story waiting to be told. This partnership with machines to listen to the cosmos leads us to a profound and humbling realization. Every flicker, every pulse, every subtle shift in the color of light, we have learned to decode points to a single, unifying truth. The universe is not a still life. It is a motion picture of staggering scale, and we have only just learned how to watch it. For millennia, human beings looked up and saw a celestial vault, a perfect and eternal clockwork of fixed stars turning in predictable cycles. That vision offered comfort, a sense of permanence and order, but it was an illusion born of our brief lifespans and limited senses. The reality revealed by these whispers of light is far more magnificent and unsettling. We do not live in a frozen museum. We inhabit a living, breathing entity with a childhood, an adolescence, and a future we can only begin to guess. Those ancient observers saw the stage. We are now watching the play, a drama written in the language of physics and performed over billions of years. The gentle heartbeat of a Cepheid variable is not just a measurement tool. It is the steady breath of a star in its middle age. The catastrophic flash of a supernova is not a random flaw in the heavens. It is a pivotal scene, a stellar death that seeds the galaxy with the elements for new worlds and new life. When we detect the redshifted glow of a galaxy racing away, we are not just plotting a point on a graph. We are watching the very fabric of the stage stretch and grow in real time. This transforms our place in the narrative. We are no longer mere spectators sitting in a distant, silent auditorium. We have been given a seat backstage. We can watch the set being built, see the actors put on their makeup, and hear the director's cues. The ability to witness a planet's shadow drift across its star connects us to an event unfolding right now, even if its light left there 100 years ago. The detection of the cosmic microwave background connects us to the opening act, the first hot, dense moments after the curtain rose. We are, for the first time in our history, witnesses to the full arc of cosmic evolution. We can trace the line from the formless fog of the Dark Ages, through the ignition of the first stars, the assembly of galaxies, the birth of solar systems, to the quiet orbit of our own world around a stable, middle-aged sun. This perspective is deeply humbling. It reveals our moment in time as wonderfully, terrifyingly brief. Yet it is also awe-inspiring, for it means we are the part of the universe that has become complex enough to look back at itself and begin to understand its own story. The subtle variations in light are more than data. They are the threads of continuity, tying our present moment of curiosity directly to the violent birth of atoms in stellar furnaces and the gentle drift of dust in interstellar space. We are not separate from the cosmos we study. We are its growing awareness, listening to its whispers and slowly learning to comprehend the grand and dynamic symphony of which we are a small, but conscious, part. Our ability to listen to the cosmos finds its deepest meaning when we follow a single story from beginning to end. Let us trace the biography of a massive star, a giant born to live fast and die young, and see how every subtle variation in its light marks a chapter in its epic. It begins not with a spark, but with a deep, infrared flicker within a cold, dark molecular cloud. To our eyes, this nebula is a silhouette against the Milky Way, a blot of nothingness. But to an infrared telescope performing photometry, it is a vibrant nursery. Deep inside, a dense knot of gas collapses under its own weight. The light curve here is not steady. It shows erratic bumps and surges, sudden brightenings that last for months. Each surge is a violent accretion event, a clump of material the size of a solar system falling onto the growing protostar. We are watching the star's violent, messy birth in real time, its first whispers written in the variable glow of heated dust. As the star clears its dusty cradle and begins to shine with stable nuclear fusion, its light becomes a beacon we can dissect. Pointing a spectrograph at it now, we stretch its white light into a rainbow barcode. The dark absorption lines are a chemical fingerprint. We see strong lines of hydrogen and helium, the pristine fuel of youth, but also faint traces of silicon and oxygen, elements forged in earlier generations of stars and mixed into the cloud from which this one formed. This single spectrum tells us the star's temperature, its mass, and its lineage. It is a product of cosmic recycling. For millions of years, it burns steadily, a seemingly constant point in the sky. But as it ages, its interior begins to churn with new rhythms. Here, Astroseismology listens to its song. The star's light, monitored with exquisite precision, reveals a complex set of overlapping, gentle pulses. These pressure waves resonating through its interior act like a stellar ultrasound. The specific frequencies tell us the density and composition of its deep core, revealing that it has already begun to fuse helium into carbon, a sign of its advancing years. The star's steady exterior belies the frantic changes happening within. The final chapter is written in a single, catastrophic flash. After only a few million years, its core collapses. The resulting supernova explosion outshines its entire host galaxy. Its light curve is now the most important variable signal of its life. For weeks, it blazes with a characteristic shape, a sharp rise to peak brightness powered by the explosive shockwave, followed by a slow, radioactive decay as cobalt and nickel forged in the blast transform into iron. Astronomers across the world track this precise fading. By comparing its known intrinsic brightness, calibrated from thousands of other such events, to how faint it appears, they calculate the exact distance to its home galaxy. This single star, in its death, becomes a fundamental rung on the cosmic distance ladder. But its story is not over. The expanding shell of debris, rich with newly forged elements, will eventually sweep up surrounding gas, perhaps triggering the birth of new stars. The dense neutron star or black hole left behind may one day drift in front of a background star, its gravity causing a microlensing brightening, a ghostly signature of the remnant's presence. Or if it falls into a dense cluster, it could accrete material and flare as an X-ray binary, a flickering testament to its enduring gravitational pull. This one, Cosmic Biography, from flickering infrared birth to explosive optical death and beyond, shows that the techniques are not separate tools. They are interconnected lenses for reading a continuous narrative. Photometry tracks its formation and destruction. Spectroscopy reads its elemental identity. Asteroseismology diagnoses its internal aging. The supernova's light curve measures its legacy's place in the universe. Each subtle variation is a sentence, and together they tell the complete story of a giant that lived, died, and recycled its substance back into the galactic ecosystem. We are not just cataloging objects. We are compiling lifetimes, witnessing the unbroken flow of matter from shrouded beginnings to brilliant ends and new beginnings again. The pristine light curve on an astronomer's screen is a lie, or rather, it is a masterpiece of subtraction, a signal carved from an ocean of chaos. Every whisper from the cosmos arrives drowned out by a cacophony of interference, a relentless static that must be patiently, meticulously filtered away. The first and most persistent source of this noise is our own planet. Earth's atmosphere is not a clear window, but a turbulent, shimmering lens. This scintillation is what makes stars twinkle to our eyes, a beautiful effect that is a nightmare for precision. To a telescope measuring a star's exact brightness, that twinkle is random noise, blurring the subtle dip of a transiting planet or smearing the gentle pulse of a variable star. It is like trying to hear a whispered conversation from across a room during a roaring thunderstorm. The solution is both technological and strategic. Space telescopes like Kepler or TESS escape this problem entirely by observing from above the atmosphere. For ground-based observatories, the fight involves adaptive optics, systems that use lasers to measure atmospheric distortion thousands of times per second, and flex a telescope's mirror to cancel it out in real time. But even with perfect stillness above, the instruments themselves introduce their own whispers. The digital sensors, the charge-coupled devices that capture light, have quirks. Tiny variations in sensitivity between individual pixels, the faint thermal noise from the electronics themselves, even the random impact of cosmic rays from deep space. A single high-energy particle can streak across a detector and mimic a star's sudden flare. All of this must be accounted for before a single scientific fact can be trusted. The process is called calibration, and it is the unglamorous, essential heart of the work. Before every night of observation, and often during it, astronomers point their telescopes at stars of known, unwavering brightness. These comparison stars become the baseline. Any change in the target star's light is measured not in absolute terms, but relative to these steady beacons. Sophisticated software then goes to work, performing a kind of digital archaeology. It models and subtracts the known instrumental effects, filters out the predictable atmospheric ripples, and statistically isolates the random hits from cosmic rays. What remains after this rigorous cleansing is the pure astrophysical signal. This pursuit of purity demands a staggering kind of patience. To confirm the orbit of a distant, Earth-like world might require observing its star for years, waiting to see that tiny, periodic dip repeat 3, 4, 5 times to rule out any chance of a fluke. To map the slow evolution of a galaxy's active core might involve compiling data from a dozen different telescopes over a decade, carefully stitching together their disparate measurements into one coherent timeline. The clean, elegant graphs we see in published papers are the endpoint of a long, grueling war against noise. They represent thousands of hours of observation, millions of lines of code, and the quiet perseverance of researchers who must trust in a signal so faint it is virtually indistinguishable from the chaos that surrounds it. Each point on that curve is a vote of confidence in our ability to listen. A hard-won victory in the struggle to hear the universe's faintest stories over the relentless static of existence. These whispers from the cosmos refuse to stay within the neat borders of a single science. To understand them, we must build bridges. The flickering light from a black hole's accretion disk is not merely an astronomical observation. It is a direct question posed to the fundamental laws of physics. Decoding its rapid, millisecond oscillations demands a fusion of minds. An astronomer maps the light curve, but a theoretical physicist specializing in general relativity must model how spacetime itself is twisted by the black hole's immense spin. A plasma physicist must then calculate how superheated matter behaves in those warped magnetic fields. Only together can they determine if the observed flicker matches the predicted hum of matter at the very edge of oblivion, testing Einstein's theories under conditions of crushing gravity we could never hope to create on Earth. Similarly, the steady pulse of a Cepheid variable is a nuclear physics experiment written in starlight. That rhythmic swell and contraction is powered by the delicate balance of pressure and gravity in the star's heart, a balance set by how atomic nuclei fuse together. To build an accurate model of that pulsation, astrophysicists must consult the precise laboratory measurements of how helium burns into carbon under extreme temperatures and densities. A subtle discrepancy between the predicted and observed pulse could reveal something new about the nuclear forces that govern all matter. Perhaps the most profound bridge is being built on the frozen plains of Antarctica, and in the quiet of space, where scientists hunt for those elusive B-mode swirls in the cosmic microwave background. Detecting that faint polarization pattern is a monumental feat of observational cosmology, but interpreting it is a journey into the realm of quantum fields and high-energy particle physics. Those swirls are theorized to be the imprint of primordial gravitational waves, ripples generated during the inflationary Big Bang, a period when the universe is thought to have been governed by a single, unified force. Finding them would provide our first direct evidence for physics at energy scales 1 trillion times beyond what the Large Hadron Collider can probe. In this way, a nearly imperceptible pattern in ancient light becomes a conduit to the universe's first moment, connecting the largest scales to the smallest. This relentless collaboration transforms every subtle signal. A distant star's flicker is no longer just a point on a graph. It is a portal, an invitation to test our most foundational ideas about reality in the only laboratory vast and extreme enough to host the experiment, the universe itself. The ultimate challenge in listening to the cosmos is deciding what we are truly hoping to hear. We have learned to decode the whispers of stars, the rhythms of gravity, and the echoes of the Big Bang itself. But what if, hidden within all that natural symphony, there is a single, deliberate note? This question pushes the analysis of light variations to its most profound and speculative edge, the search for technosignatures. These would not be natural phenomena, but artifacts, evidence of technology engineered by an intelligence beyond Earth. The concept transforms every flicker from a subject of study into a potential message. Imagine a star's light curve that defies all known astrophysical patterns. Instead of the smooth, symmetric dip of a planet or the rhythmic pulse of a variable, we see a series of erratic, jagged dimmings. Perhaps one side of the star grows steadily darker over centuries, as if something colossal and opaque is being assembled piece by piece in orbit. A hypothetical megastructure like a Dyson sphere under construction. Its light curve would be unnatural, a geometric shadow progressing in a way gravity alone could never produce. Or consider the spectrum of a star, that barcode of elemental lines. What if, superimposed upon the natural lines of hydrogen and helium, we found an impossibly narrow, perfectly monochromatic laser pulse, a beam of light of a single pure color that does not exist in nature? Such a signal would stand out like a single, sustained trumpet note in a forest of rustling leaves. Searching for these engineered variations is the ultimate test of our interpretive skills. It forces us to define the boundary between the natural universe and one that has been shaped. The tools are the same: photometry to catch the odd dimming, spectroscopy to find the anomalous line, but the questions are entirely new. We are no longer just asking what physical process caused this change. We are asking if it was made. While this pursuit remains firmly in the realm of speculation, it completes the philosophical arc of our journey. From learning to hear the universe's natural stories, we now listen with the open-mindedness required to recognize a story told on purpose. It is the final, quiet hope that in the vast cosmic dialogue of light, we might one day find a signal meant not just to exist, but to be understood. The rhythmic pulse of variable stars and the chaotic flicker of black hole feasts are more than just data points. They are the very language of cosmic history. Every subtle variation we have learned to decode tells a part of the same grand story. A story of an evolving, dynamic universe that is far more magnificent and alive than the still, silent vault our ancestors saw. These whispers, captured by our most sensitive tools and interpreted through patient ingenuity, have become our most powerful tools of discovery. They have given us a ruler to measure the staggering scale of space, a timeline to trace the birth and death of galaxies, and a probe to test the laws of physics at the very edge of reality. Each flicker is a sentence, each pulse a paragraph in the autobiography of everything that exists. As we continue to watch the sky with ever more patient eyes, aided by brilliant machines that can sift the noise from the signal, we know that every new variation we detect promises to unveil another chapter. The night sky is not a static painting, it is a living narrative, a continuous broadcast of change and creation. It has been speaking to us all along, in a language of light we are only now becoming fluent enough to understand. If this journey through the whispers of the cosmos has illuminated your own curiosity, we would love to hear your thoughts in the comments below. And we invite you to subscribe as we continue to explore more of the universe's deepest mysteries